and sensing with quantum intelligence. By the way, should we close the window or?
Go with the light. But as you can see, there's a remove there. So we can do it public again. I don't know much.
Anyway.
They used to be.
That's fine. Okay. Is it working? Oh, the other way around. Okay. So I will talk about two things. So the unifying topic is that basically we are trying to extract some sort of knowledge from quantum systems, but with some scarce resources. And so what do we mean by scarce resources? So what is scarce might change depending on the applications. One possibility, especially in learning problems, is that we have a limited amount of training data for machine learning algorithms. And so we have to make the most out of the few samples that we have. So I'm talking about this notion of sample scarcity. Then, so this is also true for whatever machine learning technique that you are using. But when you are dealing with the quantum systems, you have also another problem, which is the one that you have to extract first information from your quantum system. And the way you extract information from the quantum system is via some measurement. And if you are dealing with many-body systems, then there is a high cost in characterizing those systems. And typically, the amount of measurements that you perform, they are not enough to characterize that system. So there we talk about this measurement scarcity. And then finally, you also have a limit in what your the energy you are using to code your quantum system. So you have power constraints when you're coding a system, and this introduces some energy scarcity. So why do we care about all of these for learning, sensing, and in general quantum information applications? Well, what we are doing technically is that we are doing some optimization. So we are solving some optimization problem, but with some constraints. So normally, when we are dealing with optimization problems, we have something to optimize. So either a utility function or some error function, so a utility that you want to maximize, or an error function that you want to minimize. And this error function might be, for instance, nonlinear, like this f function over here. So, and in principle, what you want to do is that you want to get this minimum that here will be like below this point, so which corresponds to some point here. But then when you introduce constraints, so the whole problem changes. And so these constraints can also be nonlinear constraints, like this one here. And so these constraints can be in the form of inequality constraint, like that you have to be exactly along this surface. Or they might also be like inequality constraints that you have to be on this side of this surface over here. So if we see, for instance, the projection on the x1, x2 plane, then so this will be our optimization problem without constraints. And so what we want to get is this optimum over here. But then we have also some our constraints that limit our space to here, this region, so this feasible domain. And so here, basically what we want to get is the closest point in this domain to this kind of minimum error solution. So what I'm saying is that whenever we have a cost function and constraints, the whole problem changes, and we have to take this into account. Now, let's focus first of all on energy scarcity. So this talk is going to be about learning and sensing, but I will start with the sensing. So there is no learning in what I'm saying right now, and then I will show you how something similar can be applied for learning problems. So the problem that we are dealing with is what we introduced in this very recent paper from 2026, where we introduced the notion of Chernoff information bottleneck for covert quantum target sensing. So the idea of covert target sensing is as follows. So suppose there is an observer, Alice, and the observer wants to check whether there is some object in the space, like here is a UFO here. So the UFO is modeled as a refractive object. So basically you send some photons to this object. So some of these photons are reflected and are reflected back to Alice. And so clearly you won't get all the photons, so you lose most of the photons. And among the ones that go back to Alice, some of them are kind of dispersed in the environment. So that's why here we have this exabeam splitter in the environment. And then what you detect, what your detector collects, is not only the photons that are sent to the UFO and come back, but also some background noise. Okay? And given all the photons that come back to the detector, so Alice has to decide basically whether there was a UFO or not. So that's the standard setting of target sensing, or which is in somehow subclass of quantum hypothesis testing. But the idea in the covert scenario is that you want to probe the presence of this UFO without showing your presence to the UFO itself. So the idea is that we are considering kind of the worst case. So whatever is not reflected back to Alice goes back to Oliver Stopper, which is the alien here, that whose task is basically to spot the presence of Alice. So clearly also the photons that go back to the alien, they pass through some channel, and they also have some background noise, and for simplicity, we assume that the background noise is the same. So why this setting with the alien is interesting? Because if you look at the typical result in quantum target detection, which means this part over here without the alien, so everything which is not sent back to Alice is lost in the environment, so you don't care. So is that if you use some clever quantum strategy, then you can. So normally you cannot make it exact calculations. You can use bounds, but what these bounds tell you is that if you use quantum strategies, so quantum probe, so the probability of detection as a function of the energy, which is kind of proportional to the number of photons that you use, is decreases much quickly with the quantum techniques compared to some classical baseline. So what are the quantum techniques and what is the classical baseline? So the quantum technique is that you are preparing some entangled state over here. You send part of the state to the UFO, and then other part of the state to the detector, and then when you during the measurement, you combine these two signals all together to spot the presence of the alien. So while on the other hand, in the purely classical strategy, you are just sending coherent states with the same energy. So that's basically the same. And there is this separation in target detection. Okay, so this is well known. It's very used, but there is it's very nice from the theory because it shows you how you can use entanglement for target detection. But there is a problem.
What are the reasons behind the lower and upper bound? For example, the quantum stuff?
Well, these are just how good are your bounds for depending on the problem. So the important point is that the lower bound of the classical is above the upper bound of the quantum.
But okay, my question is like how, why is the variability?
Okay. This was okay. So this is actually a picture I took from one of my own paper where the problem is much more complicated than this. So we were kind of like reconstructing images. So not just a yes and no answer. So we were reconstructing images. So not just a single pixel, not just a yes and no outcome. An image with many pixels, and so that's the reason of the variability over here. It's just for the. I simply took a picture, but don't look at this particular plot too seriously. First of all, thanks for the question. This is very informal, so whenever you have questions, just ask. I think I have slides to speak for the entire afternoon, so at some point, for your sake and my own sake, I'll stop and yeah. So please do ask questions. Okay, so the point is, okay, all nice. We have a quantum advantage in energy. Problem is, doing this kind of experiment in the quantum setting is much harder than just to increase the energy of the classical probe. So people say, okay, I don't care. I simply increase the energy of my classical probe, and that's it. It's much simpler than to use all of this entanglement stuff. Okay, so true. So what we are saying is that this setting changes completely whenever we have an inverse Doppler, because if you are increasing the energy to probe the presence of the UFO, then clearly also the alien, you are also making the life of the alien much simpler, because you are showing your presence to the alien as well, right? So this kind of trick of classically increase the energy doesn't apply anymore in the covered set. So that's somehow the main motivation for us. Then, of course, nobody had in mind any military applications over here. It was just for scientific fun. And also, as applications, there is really no need for a real adversary to justify this protocol, because also assuming that there is an adversary is just a trick to find and try to study what are the most efficient protocols. Why? Because you're assuming that all of the energy that you are not using is actually used against you. Right? So it's like it's kind of a worst case assumption where all the energy, extra energy, not necessarily is used against. So that's why I say that there is no need for a real adversary. It's just to study what are the ultimate limits. So how do we formalize this process? Basically, we introduce two different hypothesis tests. So there are two hypotheses. So one is the hypothesis that Alice has to solve. So on Alice's side, there are either two hypotheses or many hypotheses, depending on whether you're interested in spotting the presence of the alien or whether you want to spot where is it actually. So in this most complicated scenario, you have multiple hypotheses. Like hypothesis 0 is that the target is not there, so there is no enemy, no UFO. So the hypothesis 1 is that the target is in some position 1. So here what you do is that you discretize the space and you assume that hypothesis 1 is where your target is, I don't know, somewhere over Palermo or over Catania or somewhere else. So that's hypothesis 2. So the target is there, it is another position. And so this is the hypothesis on Alice's side. On Eve, you have another hypothesis, which is basically Alice is not there, so there is nobody trying to spot your presence. And the hypothesis 1 is Alice is there. So whenever we have a hypothesis testing like this, you can define the asymptotic probability of error. And it is known that the asymptotic probability of error decreases roughly exponentially with m. M here is the number of probes. So how many times you are probing your target, which is basically proportional to the bandwidth or the photon number of your signal. So in the simplest case, and this psi over here is what is called the Chernoff information. And if you have two probability distributions, the Chernoff information is written by this quantity over here, where you have to maximize this quantity over here with respect to
right here, the number of probes would be the number of states probe you use.
The number of probes here can be the band, for instance, the bandwidth, so the number of frequencies, the number of modes, for instance.
The number of modes in a row.
Yes, so M here is controlled by Alice. Okay. So Alice can say, okay, I don't want to use too much M because otherwise Eve can spot me. So M is under control by Alice. Yes, that's an important point. So we have these two hypotheses. So the task is that we want to make Alice succeed, and we want to make Eve, maybe the alien, fail. Can we do that all together? So that's also why we introduced this notion of sensing convergence trade-off. So we want to make basically the probability of error from Alice's side pretty low. And so what we want is that we want to maximize this churn of information on Alice's side, because if we have like a large churn of information, it means that also with a small n we can make this error pretty small. So we want to maximize churn of information on Alice's side, but with a constraint. And the constraint is that the churn of information on Eve's side is bounded by some quantity that I call D. So the solution of this optimization problem defines a curve, which is what we call the churn of information bottleneck curve, which is a curve that connects so the churn of information on Eve's side and the churn of information on Alice's side, and this S here is basically the class of your probes. So for instance, the amount of energy you are using to probe the system. So this is basically the upper limit, because you have this inequality constraint. So this gives you the upper limit. So this information bottleneck curve defines the upper limit on the Alice churn of information for a given churn of information from each side. And so here we have plotted this quantity for some numbers over here, and you can see that whenever we use a two-mode space vacuum, meaning entangled states between between the probe and the detector on Alice's side, so you see that the allowed churn of information on Alice's side is significantly higher than what you would get with coherent states. Okay. And then here is just a baseline. We plot where somehow chi of A is greater than. So this is just so when these and these are the same, and you see that basically using coherent states, so the churn of information on Alice's side is actually even lower than the one on Eve's side for this one. So this is in an asymptotic setting, but then how can we claim whether this advantage can really give you some measurable distinctions in the probabilities? So we formalize this in this following. So we formalize cover setting in this way. So on Alice's side, we want the probability of error, which is given by this quantity, is small. So remember that Alice has the freedom to choose M. So this is kind of fixed by the physics of the problem. Alice, on the other hand, can choose this. Okay? And we want that basically, so this is the probability of error on Alice's side, and we want the probability, which we want to be a small quantity, and we also want the probability of error on the Eve's side is something large. Okay? So this has to be small, this has to be close to 1. So delta is not a small quantity. So because so this is true whenever key E is small. So we are interested in this kind of region in this curve. So when this is small, so we might wonder that if we expand the churn of information in this area, that's exactly what we need to study this problem. And that's exactly what we have done. So if we expand the churn of information bottleneck curve when D is very small, and we get some dependence, so like some coefficient lambda, and then some like power law scaling, then we can basically put these two errors all together, and what you get is a connection between the error on Alice's side and the error on Eve's side. So this is, you want this to be small. This is something small. So clearly, the exponential of something small is not good. It needs to be large. So whenever this m, so if gamma is equal to 1, namely if this curve is linear, then it is not possible to achieve this equation, because this is small. So if you have the exponential times a small quantity, this has to be 1. So covert sensing is not possible if this gamma is equal to 1, namely if the dependence is linear, while covert sensing is possible when somehow the curve is sublinear, so namely when this gamma is smaller than 1. And you can see from here that in the case of for entangled states, this curve is sublinear, is like a square root. Here, on the other hand, it is linear. Yeah. So what we found by studying this quantity over here is that for classical coherent probes, so this curve is basically linear. So covert sensing is impossible. While in the quantum setting for entangled probes, we estimate this gamma like 1/2, and so covert sensing is possible. Okay. So, and then also we studied the dependence on this n, and we have shown that somehow we can, by playing with these numbers, you can always keep the probability of error on each side close to 50%, maybe that it's like random guessing. While you can also make the probability of error on Alice side as small as you want. Okay, so that's just to conclude the first part. We have like a sort of quantum advantage in sensing, because covert sensing is only possible with quantum probes. It's impossible, at least in this asymptotic setting, with classical probes. And so this covert sensing allows us to define the most efficient protocols by assuming that all this unnecessary information is against us. We don't really have to have an enemy. And what we have introduced in this paper is a general framework to study and optimize covertness using this notion of quantum channel information.
What is the validity of this?
Sorry?
What is the validity of this asymptotic formula you have here?
It's basically the validity of the channel information, which is again the limit where n is pretty large.
What I meant is so. It's not possible that for small m there is some finite m effect that sort of go against this result, or in general this
might be. So this is like an asymptotic analysis in the limit where n is large. So there are also possibilities to study finite size effects, and the mark is a bit different. We did it in another paper, we haven't studied in the covert setting. So of course it would be very useful to study finite size effects. The response is that I don't know. It's an interesting question. So what we have done here is just in the asymptotic section.
One question. So in here you send a state to the UFO and another one to himself after the other comes back. But the noise is only for the state when he comes back.
No, the noise is also for Eve.
No, okay, I understand. But like for Alice, there is no noise in the path between Alice and the UFO.
Oh yeah, because we assume that somehow that's already modeled in a row. So that's the model that we did study. It's a model we did consider even together with experimentalists from Torino that was also describing the experiments. So for me, for theory man, that's just the model. Sure, we could also put some noise over here.
That will not change much.
No, because it's just gonna rescale somehow.
But did you consider an isotropic state or something like that? Did you consider an isotropic state or something like that?
It's a two-mode Swiss vacuum. So it's like a sweet state.
And then I guess you do some sort of joint measurement
Exactly.
between the two.
We do a joint measurement between somehow
one start of the state that called noise down, and the other one.
Now, I'm saying this in a very simple way, but this is very hard for experiments because you need to keep this half of the entangled state in a quantum memory to protocol this experiment. We are theorists, so we don't care.
I guess so.
So, just understand. When you say that you don't want the alien to detect Alice, you mean that basically there is states that are generated regardless of there being values or not, and rho is like an operation that values might or might not apply to a fixed
Exactly. So
state.
we
Right?
live in the room temperature, so there is a huge amount of background noise, which is this UV photons over here. And so basically, if you inject a few photons, I mean, it's just a tiny bit more of the background noise.
Okay.
So Alice, so Eve cannot spot it.
So the goal here is for Alice to
So
be
Alice
able to
can-
solve the problem without generating too much entanglement, basically, with the alien. So that
You can also use entanglement in such a way that somehow, so you're sending a thermal state anyway, and the idea is that somehow what you're sending is basically distinguishable from background noise.
But what if the if measures?
See?
If that's some local measurement,
That's what she does.
that's taken into account.
Yeah, she does local measurements on the signal that comes from Alice, but also this background. And you cannot avoid, because clearly if you get rid of the background noise, then even
Yes.
you can see it. But there is always the background noise. That helps.
It's kind of useful, necessary, because at large shot and shots, that's kind of
Yeah, that's what it shows.
Are you also assuming that Eve's position is close to that?
Possession?
Like it seems that if Eve's position
Position, yeah.
is between Alice's star and the thing that's being sent and the UFO,
Yes.
it cannot be covered anymore. Right?
It's so that's why we have to somehow two losses, which can be pretty different. So normally this is larger than this.
You're not assuming that Eve and Alice have the same noise?
No, I mean Alice is much further away than Eve. So then somehow this is so this loss is much higher for Alice than Eve.
In the final formula, what is the dependence upon this noise, or what
It's
terms?
very complicated.
Okay, it goes into
Exactly. So I don't know how does it scale with. So actually we do have some analytical forms because all of these are just option states at the end. So we do have some analytical form in the paper. I think we're going to so you can check the paper if you're interested. The explicit dependence on this one. Okay, so let me move. So let's see. I'm lower than what I expected. So let's go back to the second part of the talk, where on the other hand we apply something similar to learning problems. And indeed, this notion of information bottleneck is something that we did apply for this target sensing, cover sensing problems, but it's not something that was developed there. So this idea of information bottleneck is something that we took inspiration from, especially from classical supervised learning literature. So let me explain you how something similar can be done for supervised learning. So this is the setting. So we are now focusing on classical supervised learning. So you have so what you want to do is what you want to learn a mapping from some input space like images and like some output space, which is the one of labels. And we do that using some examples. So like in the standard supervised learning approach, so you consider like a number of training data. So for me, n over here is always going to be the number of training data. And so training data, for instance, here are just images of cat. And then you train the model, and then you validate or test the model with some new image, like an image of a cat. You ask the model, is this a cat or not a cat? So the probability that this model gives you the wrong answer is something that we can estimate theoretically. So it depends on the square root of the number of training data. And then some quantity over here, P, which is a kind of effective dimension, which kind of measures how complicated is your problem. And so if the number of data is much bigger than basically this effective dimension, then you can learn the problem easily. Now, suppose that we try to do that classically using a deep neural network. So how can we model the deep neural network using information theory? Well, suppose that you have data. So X are the inputs. So Y is the true output. What you do is that you send the input X to a neural network. So this neural network has many intermediate layers. And then the neural network outputs some prediction, which is Y over here. Now, you can view this using information theory. So when you somehow, when your information propagates through the network, so every time you can see this as a kind of Markov chain. So every time you are losing some information about the input. So clearly the neural network cannot give you some details that are not in the model. So what happens is that the entropy of X is actually bigger than the information between this layer and X. So you're always losing information while going through this direction over here. And so at the end, so the mutual information between your prediction and the input space is going to be lower than this. So basically what the neural network does is compressing your input space, like the space of images, into some intermediate representation, which is everything here in the layers, and eventually giving you this Y out. Now, during training, what to do? So during training, you want to kind of make this Y as close as possible to the true Y. And we can also see this in the language of information theory. So the information between the X and the Y that is present on your data set is always going to be bigger than the information between all these layers and your label. And so because of this, the information between your prediction and the true label is going to be smaller. Okay? Now, this is, so you see that we have two quantities. So the mutual information between the Y and the X, and the mutual information between the Y prediction and the true Y. So let's see if you now try to train the neural network and plot these two quantities over time. That's exactly what they did, for instance, in this paper. So here you can see the result between the mutual information between X, which is your image, T, which is some layer. So they are studying, for instance, the teeth layer over here. And then you're also studying how from the teeth layer you can recover the Y. So here you are kind of following a gradient descent. So initially, for instance, you were starting here, namely the neural network, the untrained neural network has basically no correlation with the prediction. But then whenever you train, you increase the mutual information between your neural network and the prediction. And then something interesting happens. So there is a kind of phase transition between an initial phase where somehow the model fits the model. So where somehow the mutual information between the neural network and your prediction increases. And then there is a certain turning point, which is this green point over here, when the neural network stops learning and it starts compressing the data. So you see, we are coming back. So coming back means that we are kind of learning to discard the irrelevant information that we have in our image to check whether there was a cut or not a cut.
What is the x-axis?
Mutual information between the input and the teeth layer in the training and the neural network, basically, as a function of the layer.
Of teeth.
Yeah, as a function of L. Basically. Okay. Yep. Now you see here there are three plots. So in this plot you have 5% of down. So what happens when you have so few data points is that, okay, it learns, but at a certain point, you see it's going down. So going down means that the network starts to overfit. So it's like fitting noise, not learning in feature. On the other hand, when you have like more data, you see it's learning and it keeps kind of increasing. And then whenever you have basically all the data, the network learns, and then especially from here you see it learns, and then while remaining with perfect accuracy. So when you increase the epochs, you see the colors here means the epoch. So you follow this, you are following gradient descent. So first it learns, then there is a kind of transition, and then it starts compressing it up. Okay?
When you say you follow gradient descent, going from down to top, right?
Yes, and then here is an average over many repetitions.
Which one is the average?
Well, you see here that you have many things.
So every plot there is a different realization, not a different epoch.
The epochs, so you always follow this over here.
And the other one is different realization between data sets and training process.
Yes, exactly. But the important thing over here is that if you keep training, even when somehow your model perfectly fits the data, you're still doing something else because the model is kind of compressing, learning to compress your data points and make a better prediction.
So it's like every layer has kind of a visual information with the input.
For this particular problem, yes.
With the output or with the result?
With the
top means the y is the.
So the y is the 2y.
The 2y.
Yeah. So whenever you're check, so this is the last layer. So the last layer is basically the thing that matters here. Right? So you're seeing that somehow you have this this kind of prediction, and then it's kind of learning. So this is the y. So this is not the layer, but the one at the end is the one that matters for the prediction.
So in all of these plots, at the last layer.
No, sorry. This is wrong. So here is just the y, so the number of bits to compress the input. So this is the mutual information. So the different lines are for the different layers. I don't remember exactly whether this was the first, second, or third layer. I think something like that.
And why do they go to the left?
Well, that's the trick. That's the important one. Because afterwards, it starts compressing the input. Then you might ask yourself, but why is compressing the input? Well, I mean, that's also the connection with the information bottleneck. So you might want to see what is the ultimate curve that you can get from this language. This is what people have realized. So there is a curve, a region in this plane between the mutual information between your model and the predicted y, and the mutual information between the input and your model. And so all of this area here is reachable. This area over here is not reachable. So you cannot go over there, no matter how good your model is. And so the way to define this transition line is via this kind of constraint optimization problem. So here you are minimizing the mutual information between the input and your model, and you do that assuming that somehow from your model you have enough information from the y, from the label y that you want to get. Okay. You can also rephrase it in a different way, so like maximizing this with some constraint. But then the question is, okay, so why do we want to minimize this quantity? Because at the end, the only thing I care is this quantity, which is how much my model is correlated with the real y. Well, the reason is this one, because you can show that these generalization errors depend on the number of data times some quantity which looks like an effective dimension, which is the mutual information between the x and the x hat, which is the model. Okay? So the smaller this quantity is, the better your model generalizes. So what's going on over here is that first the model starts fitting your data, and then it learns to generalize. So once you fit the data, it learns how to generalize to higher data. And that's just using gradient descent. Okay, not putting any regularization. So just reading the set is doing all the tricks in the classical set. Okay.
But the data is there's PCI or something.
There is not no PCI.
Just putting the raw data.
Put the data grid in the set.
Okay.
You mentioned you got this slide, the previous slide. Yes. So the mutual the mutual information between X and the estimated hat X is the model, you said, right?
Yes. So the hat X is basically this. So it's just
Predicted out.
all the layers.
Okay. Okay. So you want this mutual information to be high.
Small. So you want basically to learn to discard information. You want to learn what is irrelevant in your images.
But at some point you will want mutual information between the input and the Y to be high.
Sure,
or
that's exactly.
It depends on the task as well.
Exactly, it depends on the task. But then, so this is kind of notion of complexity in general, in going beyond the training set. So like extrapolating from the training set. Okay, so what we did in this paper, which is now 5 years old, is that now we applied similar idea, but for quantum learning problems. So here, basically what we did is replace these intermediate layers with a quantum layer. Okay? So the idea is that we still start from classical data, X, but then the encoding is done through some quantum state. So you have some quantum state that depends on the X and also on the hidden Y. So this can be written as an encoding. So like with encodings, you can associate some mutual information between the quantum state and the X. And then from this state, you want to do some measurement, and the task is now to recover the Y. Okay, so we have an encoding part where your classical data is mapped with the quantum state, and then a decoding part where the quantum state is kind of probed or measured to give the Y.
But rho does not depend on, why does rho depend on Y?
It's just a notation. It's just a notation because somehow it's Y that depends on X. So if rho depends on X, it comes depend on Y. It was just to make the more complicated case where somehow there is a stochastic dependence from X to Y. But okay, ignore it. It's confusing. So what is the setting? So the setting is that we have a classical input X, classical feature Y, and the point is that by varying X, we can explore different states. And the reason why this is a bit different from sensing problems is that you want to extract Y for all the possible X's, not just in an average setting. So for each X, you want to extract Y. And we do that again in a supervised learning approach. So we have access to labeled training states. So we have some row of X from some X that we can control. And the number of training states, so the number of this X that we have, is kind of big N. And what are the limits in the accuracy? So this is basically the picture that we did in this paper over here. So we studied basically what happens as a function of the, let's say, complexity of the state. So normally, the more you train the model, the lower the training loss is. So if you increase the complexity of your model, like number of parameters and so forth, the training loss normally decreases. And if the model is complex enough, you can achieve basically the Bayes error, which is the minimum error compatible with basically the statistics and the noise in your model. And what we have shown is that the distance between your model and this Bayes kind of risk is a quantity that basically depends on the mutual information between your classical label Y and the quantum state space Q. So all this mutual information are computed with respect to this classical quantum state over here. So this basically tells you this error over here. Now, if you train the model with some data and then you want to test the model with some new data, so what happens is that there is an extra error. So the error between the testing set and the training set. And this error, which is the generalization error over here, is also something that depends, like in the classical setting. This is what we have proved. So there is an error in the quantum setting that depends on the mutual information between the quantum state space and the classical input. Again, divided by the number of training data. So for us, this is like our effective dimension in the quantum case. So we want a number of training data which is much bigger than this to be sure that somehow the model converges. So this is an upper bound. So maybe less is enough, but not. So maybe more is enough, but not enough. So the other way around. Now, so first of all, let's try to clarify what we are doing over here. So we take an X, we encode that into a state, and then what we are learning over here is the mapping from the state to the Y. Okay? So we are not interested in the mapping between X and Y. That's also what most people are doing in quantum machine learning. So the encoding is just a trick for them. For us, we want to learn the measure. Okay? So we wanna, because we wanna learn what kind of measurement we should perform on a system in order to extract the feature value. So there are two ways. So either we do a stochastic decision based on some P over M, where we have some P over M, or we make deterministic decisions. So we measure some expectation value, and then using some function of the expectation value, we estimate our value. So these are, let's say, the two different settings. And so let me show you some applications, okay? Because all of this is quite kind of abstract so far. So one example is detecting phases of matter, like quantum phase transitions. So the idea is that you have X are like the classical Hamiltonian parameters, like magnetic fields, anisotropy, scattings, whatever is in your model. Rho is the ground state, and so this ground state can be in one of the different phases of matter, which is the Y, and you want to extract the Y. Okay, so that's what we did in this paper. We also have some numerical results. I won't go into the details. I mean, I'm happy to chat with you later, but I won't go into the details over here. But what I want to show here is that we have computed this mutual information between the X and the Q, which defines the generalization error, and also defines how many data do you need to learn a kind of an observable, like an order parameter to the phase diagram. Well, you see, if you start this quantity as a function of the number of spins, you see that it grows basically, I would say, linearly. And so, using this, I mean, we can claim that problems like this are learnable for quantum machine learning. Now, this is all numerics, so we don't know what will happen in the somehow some crazy limit, like a thermodynamic limit. That's why now we are doing some other paper with some other student. So we are working on free Fermion models. So models for which there is an analytic solution. So we are able to estimate this using some free Fermion techniques. And so now we are also studying the asymptotic scaling with a number of scales. But that's still something that we are working on. Now, another application is for quantum neural networks. So in quantum neural networks, normally what people do is they take an image, they encode the image in a quantum classifier, like a quantum circuit, and then from the measurement at the end, you can basically predict the class, whether it's a cut or not. And people realize that quantum neural networks can always be written in a kind of Fourier-like series. And then basically what we found is that in this setting over here, we need to study this kind of Fourier matrix of the model. And from the spectrum of this Fourier matrix, you can estimate this quantity. So clearly the number of frequencies is an upper bound. So if you have a quantum neural network with many frequencies, then it's going to be bad. But we can also get better bounds by studying any entropy of this spectrum. Oh yeah, something important that I didn't say is that in this bound over here, we don't have the von Neumann, let's say, mutual information. We have the Renyi mutual information. That's because of the map. Okay, that's the result we have. Maybe you can be more clever than us and get the mutual information here, like with the classical setting. So we were able to get the Renyi mutual information. So that's why also here we got the Renyi entropy, not the standard Shannon. So what's the intuition over here? So the intuition here is that if you have like a classical probability distribution, like the probability distribution of the cat images, and you encode that distribution with some quantum states, then, I mean, known inequalities tell you that the von Neumann entropy of this classical mixture is upper bounded by the Shannon entropy of the mixture plus an extra term. But now, if you're encoding your data into pure states, this term is not there. So this means that now this quantity has to be always smaller than the entropy of the mixture. And another good point is that, so whenever you have something like this, so this entropy, you can also compute this from the Gram matrix or the kernel matrix, which is basically the matrix of the overlap between states. Okay? So all of these quantities are computable just by focusing on the overlaps between quantum states. And so this quantity can be smaller than this when? Well, when basically we are encoding information into some non-orthogonal states. So why this is important? Because you know that somehow even a single qubit has basically infinite capacity to represent your data points. You simply can put your cat images into different points in the block sphere. But you cannot retrieve that information because of Holemov's theorem. But in some sense, so for us, that's not a problem because we don't want to retrieve the label y. We want to retrieve the label y, not the input x. So the intuition is that so we can have good learning in the quantum setting whenever you have a large mutual information between the label and the set of quantum states and a small mutual information between the input and the quantum state. So states belonging to the same label, which are here yellow, so with the same color, they should be somehow nearby in the Hilbert space. Okay, so that's the intuition. And then in this recent paper, for instance, we tried apply this idea, for instance, for quantum image representations. So we tried different way of encoding 2n times 2n matrices on the using n qubits. The mapping basically works like this. So you are writing your image as a superposition between pixel position and color position. So you see that, for instance, this Gram matrix, so the matrix of overlap, is, pretty different from 0 also in the off-diagonal terms, which means high compression. So, for instance, we tried different representations like tensor networks or others, and we found that irrespective of this kind of that we have lost, so irrespective that we cannot retrieve the image, we can still retrieve the class of the label. And that we tried, for instance, images from MNIST, fashion NIST, and so forth. And then we also studied somehow the complexity of different resources. But again, I won't go over here. How much time do I have? I guess I'm basically already over. Yeah, so I'll try to finish in 5 minutes, perhaps. Then, I mean, in this paper over here, I studied also something else where we study some temporal processes like the stock market. Let's say X is the past observation and then Y is the future. And so, so you want to predict the future given the past. And what I have shown in this paper is that somehow the mutual information between your past and the quantum memory can be much smaller than the mutual information between the past and the classical memory, using some tricks based again on this non-orthogonality. And one can use that for improved classification. Then we are also doing some other paper where we apply this to, well, kind of language models, where the task is to predict the next token, not just the stock market. And I hope we will give their cards soon. And then, okay, so now, I mean, I was planning to talk about the measurement scarcity very quickly. So far, I've never studied how many copies of S do you need to learn this data. So now we have two problems for generalization. So the number of data, so the number of X we need to explore, and the number of times we have to probe this state. So nobody knows what is this error over here as a function of, so this is still an open question. So, I mean, we have some results in this paper where we show that if you use a complicated quantum algorithms based on basically phase estimation and some other tricks, you can avoid the exponential complexity and just have an error like this. But normally you don't want to, I don't know, put all your training states in a quantum memory together with a test state. So in a simple setting, which is, I guess, similar to what some people are doing here, like in extreme learning machines, you have some X, you create your state, then you take some fixed measurements, which and gives you some outcome, and you want to learn the mapping between these measurements and the Y. So here in some settings, somehow the problem becomes simpler because you can take this part over here and model it as a classical probability distribution. So here in principle, we could apply the information bottleneck ideas. We haven't done that. But what we have done is this paper over here is to apply our bounds. And here we get an error which goes as N, so number of X's, S, number of shots, and then this kind of effective dimension that depends on somehow the complexity of this.
But you said N is what here?
N is the number of, it's like the number of training sets. So remember here we have this X and Y always. So we have different X, so we want to extract the Y for all the possible X's. Like you want to extract the phase of the ground state for all the possible input parameters. And then, I mean, okay, so we apply this for entanglement detection just to show that it's hard. So let me jump to the conclusions. So clearly, I don't have time to talk about out-of-distribution generalization. But what we did in this paper over here is that we have shown that so we can learn optical quantum channels very well for some low energy, and then have some performance guarantee to extrapolate for all the possible high energy and so forth. So I'm happy to talk about this, but let me, if you're interested, of course, but then let me jump directly to the conclusions because I'm already over time. So, so what we have done, so extracting global features from quantum states is of course a complex task, but we have shown that it can be done efficiently in some cases, for instance, for learning some phases of matter. So the driving principle for us is that generalization is favored by discarding information about the input that is irrelevant for predicting the output, and you're actually learning what is irrelevant. Of course, you don't know what's irrelevant in the first place. And some classical data can be better compressed into quantum states, and this is at the heart of more efficient learning. Then, okay, a few measurement shots can be the dominant source of generalization error. I have no time to show this. And then also this non-orthogonality of quantum states is the key ingredient also to be able to extrapolate from low energy to high energy. I didn't have time to talk about this, but it's in the PRX quantum that you can find on our Okay. So with this, I conclude, and I thank you for your attention, and sorry for your time.
Any question? I have one. Can you, I didn't quite understand the bound with the exponential of the random mutual information. How general is this? Like, what does this assume something about the underlying problem, or? Yeah, basically this one, with or without the
this is a kind of a worst case. So this is based on distance between k and y, between